Welcome to Marshable Math. Let's just see how quickly I can shoot this video. If I get it all in one take, I'm going to be very, very happy. I have to leave in about 25 minutes for another appointment. But today's video is going to be on Galileo's exploration of pendulums. So get your pencil, paper, calculator, and let me share my screen with you. Oh, I forget the desktop shortcut. That's it. Okay, good. All right. So, no. There's going to be mistakes galore. Before I do this, it's about pendulums. And so I want to just give you a brief little introduction about what a pendulum is. Here's actually a very special pendulum of mine. This is my Galileo resonator pendulum. And it's got 3 different masses suspended by strings. A pendulum is just a little mass on the end of a string. Maybe you can see that here. It's just going to be going back and forth. People always ask, like, well, what do you change on a pendulum to change the time in which it goes back? That's not necessarily the linear speed of which it's going back and forth. But people most of the time think it's the mass, that if you put a heavier mass on here, it will swing slower. Slower meaning in less time to go back and forth. That's not true. The only thing that changes the time of a pendulum is the length of the cord. So maybe you've been lucky enough to be in a childhood swing set where you in fact were the pendulum. Did you ever try to get you and your buddies to be swinging at the same time? And if so, how would you do that? I wasted so much time in 3rd and 4th and 5th grade trying to do that. And it had nothing to do with the weight. It had to do with the length of the chain or whatever it was that was holding it. So we're going to have a mass suspended by a string from this little stand that I've built, and you'll see here in a minute about what's going on. But you need to see this at first so that you know what we're talking about. Maybe if you're lucky, I'll pull that one out in class and I'll show you why it's so special. But anyway, what are we doing now? Here we go. Sharing my screen with you. I need this. Going to throw that over there. You should have this piece of paper. This is going to be your lab sheet, so to speak. Your first and last name goes here. My first name, I have a gnat in the room. If it flies up my nose and if I snort, I'm just going to apologize in advance. My first name is Mr. My last name is Marsh. You put your first and last name there. What's the question? The question is, what's the relationship between the length and period of a pendulum? A period is a special name for time. The period for things that repeat a pattern over and over and over again, cyclical things. Period is the name given to the time for one complete cycle. Like in class, I would say, what class period is this? And it's either the 1st, 2nd, 3rd, 4th, or whatever. This is the 6th class period of the day. How long is a class period? Oh, about 45 to 50 minutes or something like that. Usually it's not a full hour. If I say, what's the period of the second hand on an analog clock? Or the minute hand. Let's do the minute hand. What's the period of the minute hand on this clock? How long does it take to get back to the same exact spot and start over again? The period of the minute hand is not a minute. The period of a minute hand is 1 hour. It takes 1 hour to get to its original starting position before it starts the pattern over again. What's the period of the Earth on its rotating axis that goes through the middle of the Earth? That's 24 hours. What's the time it takes to get back to the starting position? There's actually different kind of days. Did you know that? There's the normal day, and then there's the sidereal day, because at the same time that the Earth is spinning on its axis, it's also revolving around the sun. The period of that motion is 365 and a quarter days. But to get back to the same position that the sun is in the sky is different than one complete rotation itself, because the Earth itself has moved a little bit. The sun is in a different location in the sky from day to day to day, and so it takes a little, if I remember right, a little extra rotation to get back around. But that's way off topic, but not really. So what's the relationship between the length and the period of a pendulum? Oh, what punctuation symbol do you put at the end of a sentence? A period. Why is that? Because it marks the end of one complete thought and the beginning of another complete thought. Okay, so now description of the situation, use to test the relationship and so forth. Draw a circle. That's the post. Draw a straight line down from the post. It's got to connect. There you go. Put a little box at the end. That's the pendulum weight. Draw a dashed line like this. Draw another box perpendicular to that line like this. That is the pendulum at a different time. And then draw a little swoopy thing right here. This is back and forth. We're going to let a pendulum swing back and forth and get the time for one complete cycle. Now, description of the situation. We are going to suspend a weight from a string and allow the weight to swing freely back and forth. I apologize very much for my very sloppy and not very beautiful handwriting, but I'm in a hurry. We're going to have to make this fast. Okay. The what are we measuring here? The time is measured in seconds, and the length measured in centimeters from the post to the center of the weight. Now, this is critical. We're going to measure length from the bottom of the post to the middle of the weight, to the center of the mass. That's going to be the length right there. Why is that? We're not going to measure to the top of the mass. We're not going to measure to the bottom of the mass. The mass itself has some thickness to it, and it behaves in terms of physics the same way if you could crush that entire weight down to a single point. That's how you measure the length. It's a quarter after, man. I'm going to go fast. Okay, initial prediction and additional considerations. We're going to shorten the length. So let's talk about this. As length decreases, time, and then you tell me, I'm asking, you take a moment and press pause on the video or whatever, and you put in there what the time will do according to what you think it should do. What's your opinion on that? What's your prediction? No data yet. Decide right now. So you got three ways, you got three answers. Time either stays the same, time will increase, or time will decrease. You decide what you want to do. Now, the independent variable is going to be the length. We're going to measure it in centimeters. The dependent, the thing that responds to what we deliberately change, is going to be the time. That's going to be measured in seconds. And now I'm going to do something that I don't know that I've ever done on a martial math video again. And that is I'm going to give you another video. This is actually going to be a video within a video, because I have video that I took in class the other day. Let's see how it goes. Alrighty, let's take some data points. You get two of me in the field of view. It's got a pink string with two loops on it. I'm going to place the mass on that loop right there. I need to get the length and the time it takes for one complete swing. I need to measure from the center of the mass to the top of the post. And it looks to me like about 44.7 centimeters. I got to apologize. The video looks like it's warpy. I think my iPad when I took this video is kind of shaking on the mount. So I apologize for the underwater effect. That was not deliberate. 44.7 centimeters. Now for the time, we're going to take the time it takes for 10 complete cycles and then divide that by 10 to get the time for one. So I'm going to start the clock. I'm going to wait until it reaches an end. Start. 1, 2. The reason we're doing the time for 10 cycles is because there's a problem with pressing the button. The human error on pressing the button is the most difficult thing. 10. Stop. I got 13.25, and if I divide that by 10, move the decimal over 1, 1.325. This is centimeters, that's seconds. Write this information down on your own, David. Now, change the length. So the length has to be changed significantly. I can't just do a little one. So I'm going to come up here to this one, which is about half. Doesn't have to be exactly half. Something significant change though. Now I'm going to come back in here and right at the halfway mark. Oh, the sound bar is in the way. I was rushing on this video. Like, looks like 27 exactly. So I'll call it 27.0. Move that back to kind of make it a bit more stable. 27.0 centimeters. And now the new time. Reset. Pull it back. Let it go. 4, 5, 6, 7, 8, 9, 10. Oh, just in time before it wobbled and hit. My luck is so good. I need to buy a lottery ticket. 10.35 divided by 10 gives me 1.035 seconds. I know it says 3, but for the interest of time, we can do it with 2. That should be enough for you to continue on with the investigation. Ta-da! Alrighty. Oh no, don't start it again. So the reason we're doing 10 instead of just one cycle is because of the human problem of pressing the button. The error involves when to press it exactly. So ordinarily in labs we would take like an average. We do it 10 times and then average them together, and hopefully the real data's in there somewhere. But with this particular lab, we can do a little sneaky trick, and that is we can let it go for 10 complete cycles, get the total time, and then divide by 10, and that way we've only pressed the button twice, and so we've really minimized the amount of human error involved. But this is the data that you should have right there. So we're only going to do it at two different trials. And now we'll take a look here. Direct or inverse relationship conclusion and justification. Real quick, direct relationships go like this. If I got the first thing compared to the second thing on x's, I would get the first thing compared to the second thing on y's. They both go the same direction. The first and the second top to bottom, the first and the second top to bottom. That means as one thing gets bigger, another thing also gets bigger. And if one thing gets smaller, the other thing also gets smaller. That's direct. Another one would be this. The first x compared to the second x is the same as the second y value. There's a reversal here. y1. That's inverse. Which means as one thing gets bigger, another thing also gets smaller. So it would be something like, I don't know, when the number of hours of TikTok you consume daily goes up, your intelligence actually goes down, which is probably true. But what happens with this one? What's going on between length between the first one and the second one? This is length 1, this is length 2. You can see that it goes from 44 to 27, it's going down. What happens to the time? This is time 1, this is time 2. It's also going down, so it's direct. And you can maybe explain why in your own justification there. Now, computational analysis to determine the correct proportion, the exponent, and the roots. And this is where it gets a bit mathematical. Let me get my mouse off the screen here. Break your lab sheet into 3 different parts. Okay. The first one, we know it's direct. It's not going to be inverse. We know it's direct. Here's the options. We're going to have length 1 compared to length 2. Is it equal to time 1 to time 2? And you're going to say, Mr. Marsh, well, what else could it be? Well, it could be this one. It could be length 1 to length 2 equals time 1 to time 2. But if I square it, because see, sometimes there's an exponent involved. Oh, no. Then we're going to try another alternative, which would be length 1 to length 2. Does it equal time 1 to time 2? But this time, if we square root the length. See? And we could try cubes. We could try cube roots. We could try all these different things. These are all the different possibilities that we might have. Now, let's just try and see which one gives us the best model. So you'll need your calculator. I'm just going to run the numbers and see how close each one gets to the other one. And I've set this up almost to be fractions. If you look carefully here, like if you put a fraction bar, there's your proportion right there. 47.7, 27.0. 47.7, 27.0. Is that right? No, it's 44. I got this gnat that I'm seeing flying around and it's distracting me. I want to grab him, but I don't want to distract you from the video. Missed. 44.7, 27.0. What's this one? 1.325. 1.325. And then what's the other time? 1.035. 1.035. Take your own calculator now and get a decimal, a final decimal for each side. I will do the same. So 44.7 divided by 27 equals, I get 1.655, I guess it rounds to 6, okay? 1.325, 1.325 divided by 1.035. This one, I get 1.2802. Now, is that the best result? You're going to look at this and go like, oh no, they're not equal to each other. Well, that's okay. They don't have to be equal. What we're looking for is the best model. This is not theoretical textbook data that's just made up to be absolutely perfect. This is real life data that we take doing real data collection, and it involves some kind of error, and we shouldn't expect it to be perfect. We want to be as precise as we can, but we realize it's not going to be exact. So the question is, what's the better model? And until I look at the other results, I'm really not quite sure. So let me now come over to the next one and let me run these numbers. Now, if you're thoughtful over the matter, you can see that these basic proportions are going to be the same except for the exponent, 44.7 over 27.0, but we have to square it, and that's equal to 1.325 divided by 1.035, and I already have a decimal for that. That's 1.2802. Now, I don't even have to use my calculator and redo this other fraction right here because I've got the decimal right there. So all I have to do is do 1.6556 and then square it. What do I get? I get 2.7410. Okay, so is this better or worse? This is obviously worse. If I've got to pick from the two of these models, I wouldn't pick the one on the right. It's not as close as the one on the left. But what about this third one over here? Okay, run the numbers again. Again, it's 1.325 times 1, 1.035 times 2 over 44.7 and then 27.0, but this time I'm going to square root it. All right, so I've already got a value over there on the right hand side, 1.2802. I don't have to reproduce that. Now, all I have to do is take 1.6556 which is the original decimal I got for that original proportion, and then square root it now and see what I get. 1.28. 6.7. Oh my gooseness. All right, so now between model number 1 and model number 3, which is the better model? Well, can you see? It's this one right here. Yeah, that's the better model. See how close they are? They're off by 6/1000th or so. That's really a better model. So I'm going to throw this one out, and I'm going to say this guy right there, that's the better model. Give the best general proportion that models the relationship. It would be L1 over L2 when you square root it is equal to T1 compared to T2. Now this is proportional reasoning. This is straight out of geometry. This is using geometrical reasoning, even though we're not necessarily dealing with shapes and so forth. Although Galileo, when he did this, did have diagrams involving shapes and circles and did all kinds of nice stuff with this. Maybe you get the chance to read Galileo's original writing over this someday. It's really pretty good. But anyway, most people don't like the square root thing. That's a little more awkward for them. So let's do an alternative. Or you could do this one. If I square both sides, I get this. If I square both sides, I'm going to get L1 compared to L2 is equal to T1 compared to T2, the period, when you square it. That's the one that we're going to do. State the relationship between the two quantities in verbal form. Length is directly proportional to the square of the period. There, we've actually answered the question. Now, I don't know that it would have seemed that way to begin with. Like, is it just intuitive that one of them goes by the square of the other one? Or if you do it originally, that one of them goes by the square root of the other one? Like, that's unexpected for most people. See, sometimes math is not just, or physics, in terms of how the physical world operates, it's not just how it makes sense to you in your mind. You have to actually experiment. And that's why Galileo kind of changed the way that we think about things, because Aristotle said, if it makes sense in my own mind as to how it behaves, then it must actually act that way. And Aristotle says, no, you have to experiment. Because sometimes the way things are far removed from the way that we might have imagined them to be. So anyway, did we answer the original question? What's the relationship between length and period of a pendulum? Yes. Now, what we're going to do is predict a new data point using the proportion and confirm it experimentally. So now what we're going to do is this. I want to know a new length. And if you've been in the classroom, that's the length of the pendulum that's hanging from the ceiling, in which you can't see where it's attached. It goes up into darkness and you can't see where it's at. What we did then in the classroom is we hung a weight on that pendulum and we allowed it to go back and forth. And the students were able to take a third time the period of one back and forth cycle for that pendulum. And I want to know how long that is. Now, you're going to have to do it yourself with your own data. And you're going to say, but Mr. Marsh, I don't know the period of that third pendulum because obviously I wasn't there. I have another video that I want you to watch, which actually has video of this third pendulum. So what you're going to do is this. You're going to take your third time. You're going to know that, and you're going to do this proportion. You're going to say L1 compared to L3 now. Because let's go back and let's use the original L1. Let's use this data point right here. You're going to say L1 is equal to L3 the same way time 1 goes with time 3 if you square them. And you're going to know this because it's in your data table. You're going to know this time because it's in your data table if you scroll up. And you're going to get a new time that you're going to get from that new pendulum video that you're going to watch. And so you're going to have this set up. It's going to be, what was length 1? right there, 44.7, and then 1.325. 44.7, 1.325. Your new unknown now is going to be L. It's going to leave it as L. You can leave it as L3 if you want to, but it's just L. And then you're going to get your new time from the pendulum, and then you're going to square that, and then you're going to do some algebra to solve for L. And you need to predict for me the length of that third pendulum. What do we got? There we go. All right. Catch up if you mustered, and then look for that third or that extra pendulum video whereby we take the time of a pendulum that's strung up from the ceiling and get your time from there, and then complete the lab report and turn it in. Oh my goodness. If you get within 5% error, you're really doing pretty good. Imagine that you could figure out the length of a string, not using a meter stick or anything to directly measure it, and it's attached to some place up in the darkness where you can't see. I bet you thought that was impossible beforehand. Nope. Not if you know some Galileo and some proportional reasoning. See you later, alligator.